welcome everyone to the webinar of today concerning barrier properties with polymers. Probably a kind of topic which everyone can relate to of us, even me, I would say, not being an expert on the subject. And this is one of our webinars on the polymer topic, where we have run almost soon a year full of webinars on metal and polymer towards the industry. Next picture, please. So, and here you see the registration list. We are not that many today, but hopefully we all will show up. My name is not on the list, but I'm substituting Madeleine Zetterlin today. And the webinar project, which you are taking part in now, is a project funded by the KK Foundation in Sweden, where we have received funding for producing these advanced webinars towards the industry to help the industry to be better prepared once the pandemic is over. And we are in mid of the project, and we are running webinars almost every second week all the way into summertime next year. And me talking is the one to the left, Stefan Brolin, working within the project, and my colleague Esan, you will meet later on, who is the project manager of this project. And the important persons of today, the presenters, is from the School of Engineering here, is Mohammed Irfan Kader, that will start presenting in a short while. And then also we have our industrial guest, Magnus Harrison from KD Federsen. It will be interesting to listen to you today. And the agenda is as follows. It's quite a short one. We are soon to start the webinar presentations, and then we will have a panel discussion today, not as a full group, that is, and then we will finish in 1.5 hours. So while the presenters are presenting, please turn your microphones off. And if you have questions, write them in the chat, and we will, if possible, address them during the presentation or at the end of the presentations. And please be active in our panel discussions towards the end. The webinar is recorded and will be available to you afterwards, but we will cut away the panel discussion, so there will only be the presentations. So once in the panel discussions, please feel free to turn on your cameras to make it more pleasant. And if you're unfamiliar with Zoom, down far to the left, you will find the buttons for the microphone on, off, and also for the video camera on and off. And then a bit further to the right, you have the chat function, where you open a chat box where you can write your questions. And please feel free to write them to everyone, as you see on the picture, or you can change and address them to me, or to Esan. Would be nice if you do that. Okay, thank you for showing up. And then by that, I hand over to Irfan to start presenting the topic.
Good morning and welcome to webinar Barrier Properties of Polymers. My name is Mohammed Irfan Kadir. I am assistant professor at School of Engineering, Jönköping University. In my talk, I will focus on the use of polymers in packaging food items. Next slide, please. The contents of my talk are given below: introduction, significance of plastic packaging, challenges, opportunities, active and intelligent packaging, and finally conclusion. Next. Polymers have actually achieved an integral part of our socio-economic life. The global plastic production has surpassed 450 million metric tons per year. The packaging sector represents about 2% of the gross national product in the developing countries. And packaging sector represents 46% of the total polymer demand in the European market. It also contributes to the same number in pollution as well. This represents the dark side of the matter. Next slide. So the barrier properties of a polymer are actually related to the diffusion process, which is related to the migration of small molecules such as oxygen, water, carbon dioxide, nitrogen, and water vapors into the polymer barrier films. This process actually involves three main steps: the absorption of permeating species into the polymer surface, their solubility into and diffusion through the polymer surface, desorption from the other side. So in polymers, the degradation of polymers is a physiochemical phenomenon that may lead to deterioration by swelling and diffusion. The covalent bonds may rupture during this process. It may lead to reduction in mechanical integrity of the polymers. And the worst effect is the lowering of the glass transition temperature of the polymers. Next. Next, yeah. So diffusion in polymers is fairly a complicated process, but it could be fairly understood by a fixed law of diffusion. So according to this law, the flux of the permeating species is equals to the product of the diffusion capacity of a polymer times the pressure gradient across the membrane. The diffusion coefficient itself depends on four variables, that is the area of the barrier film, the thickness of the barrier film, solubility of the permeating species, and molecular weight of the permeating species. So we can arrive by putting these values into the first equation, we reach to the Fick's law. And it tells us that there are 5 variables which we have to control in order to produce better polymers with better barrier properties. Please, next slide. So the barrier properties of the polymer, therefore, be controlled by the following factors: the nature of the polymer. So we can play the nature of the polymer by, for example, changing the morphology of the molecular structure. The density, although it's a fixed phenomenon, but it could be altered by changing the percentage crystallinity in the polymer, filler concentration, cross-link density, etc. The nature of the fluids. So although it is not in our control because it depends on the atmosphere, what kinds of permeating species are available in the fluids. So what we have to do is to actually choose a polymer which better suits for such kind of environment. The area and thickness of the polymer film. So this is an area which is actually which is a focus area of the research, because we want to minimize the thickness of the polymer films. So to have like a minimum use of the material and therefore have like less recycling effort which is required later on. So the fluid concentration and the partial pressure of the gases, we can control these things as well. Permeation time and temperature, these are the factors which control the diffusion and barrier properties of the polymer. And so by actually playing with these parameters, we can actually produce better polymers with better resistance to the to permeation. Next slide, please. So now we'll talk about the significance of packaging in the food sector. Next slide. Polymers are extensively used are used in packaging industry. So now the question arises, do the polymers meet the barrier requirements of food packaging? The answer is no. And this is quite strange because both metal cans and glass containers are impermeable to small molecules, whereas we see that these molecules can permeate into the polymers. So now the question is still the same, that why we are using the polymers for the packaging material, as a packaging material. The polymers only provide limited permeability depending on the polymer type and the nature of the penetrant. The main reason for selecting polymers as a packaging material is owing to its low cost and flexibility, which we can elaborate further in the next slides. Next, please. So I can give an example why the polymers are more cost efficient. So for instance, in order to produce, transport, sell, and store 1 gram of bread requires 15.8 megajoules of energy. To produce low density polyethylene bag requires only 1.4 megajoules of energy. This means that a unit of energy is in the packaging actually protects 11 units of energy in the product. Next, please. And uh, the main reason of like using the polymer as a packaging material is the flexibility. These polymers are really flexible in terms of processing and design. We can produce polymers with variety of shapes by using the conventional processing techniques. So therefore, we see that a widespread use of polymers in packaging, starting from the food packaging to medicines, chemicals, and so on and so forth. And one of the main reason of using the polymers is to have actually minimum use of the material, and it also requires minimum space as well. For example, the shrink wrap technology of the thin films allow a very tight packaging of the goods irrespective of their shape. For example, we see here a turkey is wrapped in the polymer thin film, and you can see that it is so tightly packed that we don't see any kind of space there. So we are actually making use of the better making use of the material as well as the volume as well. Next, please. Okay, the food which reaches to a consumer is actually it takes many steps, starting from the harvesting, then to the storage, transportation, and then after that, processing plant, retailing, and then it finally reaches to the consumer. But the consumer pay little appreciation to the role of packaging throughout the journey. On each step, we require containment as well as protection of the food. Otherwise, it will result into the spoilage. And this is one thing which ensures the food security globally. So we can give different kinds of example to elaborate even more the significance of packaging in food industry. In developing countries, 40 to 50% of the food is wasted due to improper food packaging. 1/3 of the food produced in the world is wasted due to poor packaging. An example which can be given regarding the role of the polymers in food packaging is a cucumber. It loses moisture so quickly that within 3 days, if it is not wrapped in polymer, it will not be able to sell. So we can see that the role which polymers are actually playing in the packaging of the food. So this is, although the packaging is the unnecessary part, which from we can say it from the consumer's point of view. So he is thinking like he is paying something extra and he thinks that it is a burden on his pocket, but this is not the reality. This is one necessary evil which is required actually in the containment and protection of the food. Next slide. So now we will talk about the general requirements of food packaging. So any material actually can qualify to be used as a food packaging material, but then there are some general requirements which a material has to fulfill in order to be regarded as a packaging material. So basically there are the five major requirements which a packaging material has to fulfill. Number one, it has to control the permeation of small molecules such as oxygen, carbon dioxide, nitrogen, and water vapors, which may result, their penetration into the goods may result into the oxidation in the food, change in texture, rancidity, change in weight. It could either the good can gain the weight or it could lose the weight. Then the second requirement is the control of absorption that may lead to change in odor or flavor or aroma of the food, which is an unnecessary thing. The third requirement is to act as a barrier against the ultraviolet rays, which may deteriorate not only the polymer, but also the product, which could result in oxidation, discoloration, and the loss of nutrients. So the fourth requirement is the ability of the packaging to resist the mechanical damage which may occur during the transportation and even by the handling of the consumer. So any loss of the mechanical integrity of the packaging may lead to the ingress of microbes into the food stuff, which may spoil the food. So the fifth factor is quite important, and it is to control the migration of harmful substances, for example, monomers, oligomers, or decomposition products or solvents, etc., from the surrounding. So these materials are not only harmful for the polymer, but the product inside the packaging also. So it's very important that the polymer must resist the migration of such kind of additives, which are sometimes unintentionally added into the substance, into the polymer packaging. Next. Packaging could be good or bad. Bad packaging not only provide inadequate protection, but may contribute towards the ingress of toxic substances from the surrounding atmosphere or migration of impurities from the packaging. Whereas good packaging acts as a silent salesman, developing confidence in consumer about the quality of goods. The modern packaging not only provide protection, but also offer different functionalities such as, for instance, heat sealing, ease of opening and closing, use of minimum space and material, environmental friendliness. Ingenious packaging design facilitate ease of use and minimize waste and good as well. Next slide. So now we will talk about some special challenges which are related with the polymer packaging. Next. So the polymers, we have to bear in mind that polymers do not provide absolute barrier towards the diffusing species. They only provide limited and specific barrier properties which are related to a specific permeant. For example, we can take the example, some polymers exhibit outstanding oxygen barrier, such as polyethylene, terephthalate, EVA, and polyamide 6. Some polymers exhibit excellent water vapor barrier properties, such as polyethylene and polypropylene. Polyamides have outstanding resistance to hydrocarbons, but poor resistance to polar solvents. Polyethylene and polypropylene have outstanding resistance to water, but poor resistance to oxygen. So EVA, which has an excellent barrier to oxygen, loses its high barrier properties in the presence of humidity, which acts as a plasticizer. Next slide. There are some stringent barrier requirements of especially the ready-to-eat foods. For most of our ready-to-eat food require oxygen transmission rate below 5 cc per meter square per day and water transmission rate below 0.01 grams per meter square per day for a 25 So, in some food packaging, we require selective permeation as well. For instance, packaging of fresh fruits and vegetables demand the permeation of carbon dioxide, but barrier to oxygen. Next. Another property which is required from the polymer packaging is to act as a scavenger. For instance, a freshly roasted coffee releases considerable amounts of carbon dioxide formed by Maillard reaction during the roasting. And unless it is removed, it can cause swelling or even bursting of the packaging. Next. Ethylene absorbers. So freshly packed vegetables and fruit products produce an enzyme which is called ethylene. By the way, this is an enzyme which is responsible for the coloration of the autumn leaves, and also it causes the ripening of the food. So if this enzyme or the chemical is not removed out of the packaging, it can cause over-ripening and damaging of the cell structure of vegetables and fruits. Next. Some ready-to-eat food items, fruits, and salads demand high barrier to diffusion of small molecules while maintaining optical transparency. So this feature is actually very important from consumer's point of view, because he wants to know that the quality of food inside the container. So transparency is significantly important in terms of attracting the customers towards the product. So which is actually a contradictory requirement, since increase in crystallinity results in decrease in transparency and increase in resistance to diffusivity. So we have to actually cater this contradictory requirement in plastic packaging as well. Next slide. Ethanol has been used as an antimicrobial agent for centuries, with Arabs having used it for over 1,000 years ago to prevent the mold spoilage of fruits. So this is another problem, like if in the packaging material, certain substances keep on accumulating, for instance, moisture, they give rise to the formation of molds inside the container. Next slide. So then there are some other problems which are related to the moisture. For example, when we have a fresh vegetables and fruits inside the plastic container, due to the transpiration process, they absorb oxygen and release carbon dioxide. And this process actually accelerates when there is a temperature fluctuation. So this may lead to the development of actually the condensation products, which may result in formation of mold, as well as fogging of the plastic films also. So we need actually the materials which can absorb this transpiration products. Next slide. Another issue which is related to the polymers is the pollution caused by the single use of plastics. So these two examples actually tells us that how much polymers are indispensable for our life. For instance, the in first example, the Washington Post actually wrote an article that good job humans, the oceans now contain 5 trillion pieces of floating plastics. But the dark side of the matter is that Washington Post itself is actually packed in low density polyethylene. And in another example, the author who claimed actually that how the plastic could be reduced from our society, his own book is wrapped in the plastic. Next, please. So these are the challenges which we are facing today. So now what are the opportunities? How we can make the things better for our environment, and how we can improve the barrier properties of the polymers. Next. So the diffusion and solubility of the penetrant in polymers are mainly determined from three aspects. Number one, the nature of the penetrant, the structure and morphology of polymers, the surface modification of polymers. So as we have already discussed in the previous slides, that polymers only provided a very limited barrier to the diffusion of the penetrating species. And they are actually each polymer, or we can say that the polymers do not provide absolute barrier to all these diffusing species. Some polymers are good for providing barrier, for instance, against oxygen. Some are good for providing barrier against water. So now the scientists think, why not to make a laminate of these polymers, so that we could achieve absolute barrier properties from the polymers. So the modern polymer processing techniques such as co-extrusion allows us to produce multiple layers which have a better resistance to the different migrating species into the polymer. So one way of actually increasing the barrier properties of the polymers is to develop the laminate structures. In different food packaging, these laminated structures could have more than 11 layers of different polymers. Another way of improving the barrier properties of the polymers is to play with the molecular architecture of the polymer. Since we know that the diffusion of a polymer is a time-dependent process, so if we can delay the diffusion of the migrating species into the polymer, we can improve the barrier properties of the polymer. Since polymers are either amorphous or they are semi-crystalline in nature, amorphous polymers have a lot of free space called free volume in their molecular structure, which allows the molecules to penetrate easily through the polymer barrier films. Whereas the crystalline polymers provide a treacherous path for the permeating species. So the permeating species have to actually play around these crystalline regions in order to surpass them. So one way of improving the barrier properties of the polymers is to increase the percentage crystallinity in our polymers. So for example, we can see that low density polyethylene, they have not as good barrier properties as high density polyethylene, because high density polyethylene is more crystalline in nature. Another way of improving the permeability of the polymers is to use impermeable fillers. For example, the nanoparticles could be incorporated into the plastic films, which again provide a treacherous path for the permeating species to follow. And this leads to increase in the barrier properties of the polymers. And as we have discussed that some polymers have like a better resistance to some specific permeants. For example, polypropylene, it has a better resistance towards the moisture, whereas polyamide has a very poor resistance to the permeation of water vapors. So what we can do is that we can blend polypropylene into polyamide in order to improve the barrier properties of the polymers. So normally, in order to improve the barrier properties of the polymer or of polyamide, polypropylene is blended with polyamide. Last, since diffusion is actually a surface phenomenon, so what we can do is that we can create some layers of material on outside the surface of the polymer, which can act as a barrier at the first place. So for this the way of actually improving the barrier properties of the polymer substrates are coated with the barrier layers. We can use different kinds of coating techniques such as plasma or corona treatment. And for instance, chemical vapor deposition, this is one technique which could also be used to deposit high barrier polymer films on the substrates. Next slide. So, but still some food products such as fresh meat, cheese, instant coffee, they have extremely stringent requirements of barrier properties they demand from the polymers, and sometimes then polymer are actually unable to fill those demands. So then we have to think outside the box. And one way of thinking is to use active packaging. So first I need to define what is active packaging. So packaging in which subsidiary constituents have been deliberately included in or on either the package material or the package headspace to enhance the performance of the package system. So in this technique, actually, we make use of the headspace of the package, and we add different chemicals with different properties such as scavenging or absorption of the gases in the form of sachets. So you might have seen that in especially when you open the fresh meat packaging, that at the bottom of the tray you will see that a sachet which act as a moisture absorber, and it keeps the meat away from the moisture that may result into the development of the mold. So there are different active packaging systems which are used in order to meet the stringent requirements of the food packaging. For example, we have discussed the role of ethylene in spoiling the food material because it results into over ripening. So one way of actually using these one way of actually eliminating ethylene is by using a chemical called potassium permanganate in the form of sachets. But since potassium permanganate is a toxic material, it cannot be directly put into the packaging system. So what is needed is that 4 to 6% of potassium permanganate is actually fused into material with a large surface area such as silica. So, in this way, it can act as a material which can absorb this harmful toxic material. Similarly, antimicrobial elements could be incorporated in the sachets. Say, for example, we discuss about the role of carbon dioxide in the coffees. That freshly ground coffee produce a lot of carbon dioxide gas. So this gas could be eliminated from the packaging by using, for instance, calcium hydroxide, which actually catches the carbon dioxide and therefore eliminates the carbon dioxide from the atmosphere of the packaging. So and so forth, we can give like different kinds of example, like oxygen scavenger. For example, iron powder or ascorbic acid could be used as the oxygen scavenger. So there are a number of ways of actually enhancing the barrier properties of the polymer. Next slide. So we also discuss about the role of plastics in the environment. The single use of plastic is really harmful for the environment. So what is needed is the materials which are bio-based and biodegradable. So I have arranged actually the material in hierarchy which are best for with respect to environment. So the materials which are best for the environment are bio-based and biodegradable polymers. And the worst materials for the environment are worst material. So when we actually look at the requirements of the barrier properties of the polymer, even the petro-based polymers are actually unable to fulfill the demands of some food items, for example, instant coffee, fresh meat, and cheese. But still, there are some bio-based polymers which can actually act as a potential replacement of the petro-based polymers. For example, PGA is a bio-based polymer which has an extremely good barrier properties. Similarly, we see that PHBV is a bio-based polymer, which although cannot be used for instant coffee, but surely it has properties which are sufficient for packing the food such as cheese and the fresh meat. Next slide. So here I have arranged the bio-based polymers with respect to their barrier properties, and we can see that polyglycolic acid is a material with extremely good barrier properties. Therefore, we should hope that in the future we will be able to develop the bio-based material with extremely good barrier properties, although the bio-based materials are slightly expensive as compared to the petro-based polymers. Next slide. So when we compare actually the cost of biopolymers with respect to petro-based polymers, we see a significant difference in prices. For example, the cost of one of the important biopolymer, polylactic acid, is sold in the market $1.9 to $2 per kilogram, whereas PBS, PBAT, and PHA cost around 3.5 kilogram. So we see that if we compare them with polyethylene and polypropylene, the cost is only 1.2 to 1.3 kilogram. Right now, the consumer is not ready to pay the high price. So the solution is that we should find new resources which are less costly as compared to the current existing one. and we should stimulate the market so that we have like more demand for such material, and mass production of these materials could be made possible. Next slide. Now I would like to reach towards the conclusion also. And the thing is, like we discussed the all the difficulties which we face about the bio-based materials, but still these materials have like a lot of potential. For example, some bio-based materials are actually edible in nature as well. These polymers are not only bio-based and biodegradable, but also edible and eco-friendly as well. Examples of such polymers include protein-based casein that which is considered 500 times better than ordinary plastic at keeping away oxygen from the foodstuff. The initial attempts show promising properties, but difficulties in handling and water solubilities were the problems which these materials face. However, by few improvements such as adding citrus pectin into the blend to make packaging even stronger and more resistant to humidity at high temperature, make it possible to develop films. Another advantage of such films is that they can be sprayed on cereal bars or flakes and delicate fruits such as strawberries as single serving edible food wrappers. Next slide. So last, I will talk about the intelligent packaging, which is actually a new development in the food packaging. So intelligent packaging means that the packaging that contains an external or internal indicators to provide information about the history of the package and the quality of the food. So it can inform consumer about the quality of food by indicating when it is ripe, fresh, or it will stale. It can indicate temperature of the food through the use of thermionic inks, respond actively to changes in product or package environment, for example, microwave doneness indicator, etc. It can indicate the temperature history of the food through the use of temperature time indicators, where the package has, whether the package has been tempered or not, could be, it could give, it can give information to the consumer. Communicate product change information, its history, or the condition of the to the user. Assist with the opening and indicate seal integrity. Confirm product authenticity and also act to counter theft. For example, in this in the diagrams given below, we see a sticker which can be put on the packaging, and it tells about the quality of the food inside. And as we can see that the color is changing with respect to the time. So next, please. So from my discussion, you can conclude that polymers are not ideal materials for any job. And that's where my and your role comes, that is to tune them according to our requirements. So with these words, I thank you very much for listening to me, and I will look forward to your questions.
Actually, Irfan, we have a question in the chat which you might address shortly before handing over to Magnus. This is Boris asking, how long do the biological plastic retain their properties?
Okay, the answer is that biopolymers or biodegradable polymers have a mediocre barrier properties. So their properties actually depend on their crystal structure, and also the fact that whether the material has a resistance towards the moisture or not. For example, some these biopolymers, they have the ability to actually act as a barrier material, but it is actually, you can say that it is not as efficient as petro-based materials. So I don't have actually the actual numbers in my mind as well at this moment, but I think sufficient is to say that they are compatible materials, but still we have to figure out the ways actually to improve their barrier properties. And I think in all the biopolymers, we can use the same analogies which we use for the petro-based polymers to improve their barrier properties. So right now, it's probably difficult to answer that in terms of number, that how they are performing, but their properties are mediocre. So I would say that there are certain applications where you can trust these materials and you can rely on them. For example, we have seen in the graph that the materials such as PGA and PHBB are like extremely good. They have extremely good barrier properties.
Okay, thank you, Irfan. I saw we have another question from Sarah, but I think we will actually save that for some time to make sure that Magnus get his time for presenting, and we will make sure that we address your questions, Sarah, towards the end, if it's not included in the Magnus presentation. So thank you, Irfan, and over to Magnus.
Thank you, all of you. So yeah, I will also talk a little bit about this subject. I will start a little bit in the packaging area and move over to, let's say, some more technical application from another perspective. So you can switch slide. My name is Magnus Harrison. I've been working in the polymer industry for almost 25 years. Since 3 years ago, I've started the KD Feddersen Group, and the KD Feddersen Group is initially, when it started back in the late 40s, a trading house. And nowadays we are mainly, or the part where I'm working with, we are mainly serving the polymer industry. So you can switch slide. And distributing a lot of different polymers. Inside our group, we are also having a couple of companies actually making polymer compounds also. And up in the Nordics, we are selling injection molding machine, blow molding machines, and so on. What we see on the right, that is, and the highlighted material, this is the ones that we are providing. But onto the subject, and we take next slide. And I would actually like to align to the question that Irfan got. And this bio-based material is quite interesting. It's of course very important, as Irfan showed in his pyramid. We have bio-based, but not being biodegradable. And we have bio-based that is biodegradable. And if that could be part of your question before, how long time do it take to degrade this polymer? Then it's very much depending on the thickness of the part, if it's a film or if it's having a bigger thickness. And also, it's a polymer. Everything is time and temperature dependent. So key for polymers is always time, temperature. And there is a big belief that we will have this biodegradable and compostable material, and that they will solve the world. They will solve certain things, but it will not be as easy for it to degrade in, let's say, in northern parts of the world where it's cold versus where it's warm and with a high humidity, for example. So that is the challenges. For me, the most important thing is that we should have polymers where it's really needed. We should get away from it where it's not needed. So refer to the Washington paper, where they had this plastic bag around the paper. that is not something we need. But if we start to go into the packaging again, so I have a bottle here to the right, and what is the bottle supposed to do? Yeah, the key thing is to protect and preserve the product. And as I said before, it's a polymer. It's crucial that we design it for the correct temperature and the time that it should sustain and survive. And especially as properties can fail over time. It could also be here that we have something like you have light from the outside. Could be the reason why it's brown here, to take away some of that, and that destroying the product. It could also be that we have actually mechanical strains. We have a pressure from inside of the application. This carbon dioxide here could put some pressure on the bottle. We have certain cases in some areas you have these beer kegs made of plastic instead of aluminium. And there is valves, and these valves are inserting engineering polymers chosen for having good creep properties. But is that working all of the cases? Yeah, perhaps when you are shipping something to Australia and you have a very acidic product with a low pH value and a high temperature, that will be, and that's what I'm coming into, chemical resist to the product. So it needs to survive the product. So an orange juice can be very aggressive. It's an acidic material. Of course, for packaging, the majority of the packaging is food related. So we need to have a food approval or food contact approval. Also with regards to smell, flavor, it should not give or take flavor. And here, when we see all of this material, and Irfan, he was referring that he more or less said that plastics are quite lousy in some extent, but they are fantastically cost effective. And that is one of the crucial points for using polymers. It's the cost effectiveness. And then something which we should have started a little bit earlier, we are working on that, and that is reuse and recycle, and or let's say it like that. So, jump over to next picture. Yeah, so for our international guests, this is what the Swedes, they are using sometime instead of smoking. So they are having the snuff which they are putting in the mouth under your lip. You can also, very popular here, it's nicotine pouches. And I like to talk about this box. So in this box, you have your fresh pouches or snuff, and everything which is with regards to tobacco. It's very critical that they should not take any smell or taste from the packaging or the outside. So they should preserve the things that you would like to use. But here they have also solved another topic, because the risk is that you are throwing away these pouches or snuff afterwards. And then they have another solution. So you have this upper lid, and there you can put your used snuff or pouches. A perfect solution. In these cases, if we are talking about the PP material, I know, and there have been a lot of things in discussion also with other polymers having better barrier properties. But from a cost perspective, cost performance, the PP is fantastic. But there is ways of making it even better. But it's so much more efficient to use a PP, which is one of the best polymers from a performance point of view. If we jump to the next slide, and yeah, I think the majority of the people know what a lighter is. Is this a packaging? Yeah, it have multiple functions. Let's put it like this. So in this case, it's a packaging for the gas, which is actually in a liquid form. So it should withstand the gas from coming out through the container. So it's important to have a low permeation rate for the hydrocarbons. The technical part here, and where a lot of other polymers would fail, is that we have a constant pressure from the inside of this can pushing out. So we need to have what we call a good creep behavior. And that's giving us a polymer with good long time properties. And actually, we are talking here, what Irfan was referring to also, we are talking about a semi-crystalline material, which having better long-term performance. Here, it's also important to quickly assemble it. And in these cases, they are using to get this can, it's welded together to put those two things together. We can also refer to what Irfan was saying earlier also. We talk about metal, we talk about plastic. We could take the famous zipper lighter, which is a metal version, a little bit heavier and perhaps less design flexible from certain point of view, being also more expensive to make. So this is always, when we come to polymers, it is normally the price which we can reduce and the weight that we can reduce. The key benefit of a polymer. Next slide, please. Sometimes it's not the requirement from the normal market or from building up and a new requirements from somewhere out there. It could be also that we have a regulation changing it. So here we have a tank, and this case is some years old. I haven't followed the last years, but I'm quite sure that this is still ongoing. So a lot of these small off-road engines, like ATVs or lawn movers or blowers for leaves and so on, they are not allowed to let their fuel go through out from the tank. And this regulation have put more pressure on that, so it should not go out that much. We can take an example. If you, for example, have your lawn mower, you put it in to your garage in autumn and you have half a tank and you start it in the springtime. Perhaps you have difficulties to start it because the fuel is getting old. So some of it have actually migrated out on the lower molecular weights. So the key property here is, of course, the permeation, and that it's resistant to the fuel. And the fuel is a fantastic world. There is so many different types of fuels. You have diesel fuels, you have petrol fuels. Now you have petrol fuels with ethanol in different amounts, and you have bio-based diesel fuels. And all of this, the material needs to withstand. Strength-wise, we have, of course, some requirements, and we have impact and drop test on this application. We move to the next slide. The requirement here is actually not just the tank itself, it's also the tank plus the cap. And one solution here, and just to quickly explain without going into too much of a detail, this fuel is containing also some ethanol, in this case, the CE10, so 10% ethanol. And as Irfan was saying, it's important to always think that you can solve a lot of things with thickness. So what have been done in the past using a polyethylene is to increase the thickness, but that is not possible too long time. So here they have changed to a POM-based material. It's actually slightly impact modified POM, because it's a highly crystalline material and not always having the best impact properties. So there is something else in this grade, but it's possible to blow mold in the regular tool that they had before. But there was also other options, and that's what we will see on the next slide. You could potentially use your polyethylene tank and using the same blow molding tool, but treat the inner surface with the fluorination process. Of course, this can be scratched off. And we also need to be aware that the fluorination process is not very healthy. So the fluoropolymers have some issues, and we need to take care about gases and so on from the process. But if it's a lower amount of part and it's a short-term solution just to overcome the initial requirements and then develop new things for the future, it might be an option. Also, what could be possible here, it was to mix some kind of EVOH based barrier into the polyethylene in the range of 10 to 20%. It's giving some uncertainty, is it well distributed and so on, but that was one of the options. Another option was the same as we had with the packaging, work with multi-layer solutions. The drawback of the multi-layer solutions here is that was coming from a blow molding process, and if you would have a current tool for a classic blow molding, that would not be possible. But for future, with redesign and a new tool and new technique, that would be an option also. We can add different kind of nanoclays or similar, basically to make it harder for the fluid or gas to get through it, as Stefan described. It's a more complicated, takes a little bit longer time. And the last part, that was to switch from a polyolefin to another engineering polymers. I showed here a POM, an impact modified. It could be a polyamide. It could be a different kind of materials. But it leads to different challenges. And especially when we are talking about these engineering parts, which is not the packaging. The advantage with the packaging is that the volume is so big and the price is so sensitive. So you need to make a lot of parts in a very quick time. Here, when you have a lower amount of pieces, other way of doing it could be better. And you are also then challenged with fuels, for example. It could also be water application. So think, for example, if you have a water meter or a water pump where you have a part fully in plastic. You have a long lifetime, you are building it into your house. It needs to withstand the load and also the permeation. And after a while, in this, even with this, there is good, even better materials that Irfan have been showing from a technical point of view. Too expensive for packaging, but even them, as he describes, have a hard time to be 100% tight. So over time, something will happen. And that's why it's so important with time and temperature when you design your application. Next slide. And I think I'm done here, but let's see. Yes. So I am done. I saw there was some kind of question, but let's see if someone had the chance to see what it was.